Let's examine how we currently handle documents in AI. The standard approach treats text as a passive input, forcing data through a fixed pipeline. There is a mathematical mismatch here. Real-world corpora, regulatory archives, research databases, entire source code repositories are practically infinite. The language models we feed them into are finite. The industry response has been to widen the pipe. We now have models boasting context windows of 1 million, even 2 million tokens. But scale alone hits a wall. Even at 2 million tokens, complex synthesis across massive, unstructured datasets breaks down. Making the input pipe wider does not fix a model's structural inability to navigate and process massive amounts of information effectively. Take the first common workaround, context stuffing. We load an entire massive document into the model at once. It reads linearly, in a single pass. As it moves deeper, attention degrades. If new context changes earlier meanings, it cannot reverse course to reread. So engineers turn to the alternative, Retrieval Augmented Generation, or RAG. RAG bypasses the limit by carving documents into pieces. It retrieves pre-selected fragments and injects them directly into the prompt. By doing this, it destroys structural context. The model receives isolated shards of data, completely disconnected from the surrounding architecture. Cross-chunk coherence is lost. You are forced into a losing trade-off. You sacrifice structural coherence for retrieval with RAG, or you sacrifice attention detail for scale by stuffing the context window. In 2025, researchers published a paper proposing a new pattern, the Recursive Language Model, or RLM. The RLM pattern abandons feeding a document into a model. Instead, it treats the document as a queryable environment. The model uses tools to query data iteratively. It scans, searches, pulls metadata, and selectively targets specific sections to read at full resolution. To put this theory into production, I built RLM-MCP. It operates as a Model Context Protocol server. MCP provides a standardized framework that exposes a lifecycle of tools to any compatible client, whether that's Claude Code or Cursor. The LLM is no longer a passive reader trying to parse an entire novel by flashlight in one pass. It operates as an active researcher with the agency to navigate the text. RLM-MCP organizes this navigation through a 5-step lifecycle. Step 1 is session creation. Everything the model does, documents, chunks, indexes, is strictly scoped to an isolated session. Step 2 is document loading. The model can ingest inline text, files, or directory globs. To prevent redundancies, content is evaluated by its SHA-256 hash. If the exact same document is loaded twice, it resolves to a single cryptographic hash string, preventing duplication. Moving to Step 3, on-demand dynamic chunking. Standard RAG pipelines pre-chunk data blindly. Here, the LLM actively decides how to slice text, choosing between fixed character counts, line counts, or regex delimiters based on the exact task it is trying to execute. Step 4 is the search execution loop. The model runs literal, regex, or keyword queries. The BM25 index is built lazily. It does not preemptively process the corpus. Instead, the index generates in real time across data blocks only when the first query is fired. Step 5 is artifact storage. Any output the model derives from the document, summaries, extractions, or classifications, is retained here. This modular lifecycle takes theoretically infinite text and binds it into explicit, manageable processing operations. Giving an LLM autonomous querying agency introduces serious engineering risks. Left unchecked, a model can spiral into infinite search loops and rapidly drain computational resources. To manage memory efficiently, the system uses a cache staleness fingerprint. It tracks document count, content hashes, and the tokenizer version. If any of those parameters shift, the index automatically rebuilds. We also implement strict denial-of-service protections. RLM-MCP establishes hard caps, budgets of 500 tool calls, 10,000 character document peaks, and a 50,000 character response maximum. These caps prevent the model from retrieving massive data blocks that overflow its context window.
Concurrency semaphores cap batch processing at 20 concurrent loads, while async locks ensure multi-agent safety. These strict constraints separate an experimental academic pattern from a viable enterprise-grade server capable of supporting a full engineering team. For enterprise AI, the baseline requirement is eliminating untracked synthesis and hallucinations. You need to know exactly where an answer came from. This brings us to structural provenance, the primary architectural benefit of RLM over massive context windows. Instead of offering an answer in isolation, RLM maps every output back to its exact verifiable path of derivation. Every artifact is recorded with exact metadata, the literal character ranges, the unique prompt hash ID, and the precise timestamp. Provenance shifts model outputs from being probabilistic guesses into mathematically auditable and defensible artifacts. RLM is not a blanket replacement for every LLM interaction. If your document fits comfortably within a standard context window and you do not require rigorous provenance tracking, standard insertion remains the optimal path. You just paste it in. You deploy RLM when the corpus exceeds reliable attention spans, or when your use case demands rigorous, iterative, and defensible research. The RLM MCP architecture serves as an operational bridge between infinite data and finite models. Moving beyond context windows requires abandoning the idea of reading entire archives at once. Instead, we have to engineer environments where models can actively search, synthesize, and prove their work.